Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 7, Lesson 4 on factoring by grouping. This is a brand new factoring technique that you've never seen before, so let's get right into it. All right, factoring by grouping. You now have essentially three types of factoring. One, greatest common factor. Two, the difference of perfect squares, and three, trinomials. Granted, simple trinomials, but trinomials. In this lesson, we will introduce a new type of factoring known as factoring by grouping. This technique requires that you see structure in expressions, and I'll explain what that means in a moment. Let's dive right into it in exercise number 1. Factor a binomial common factor out of each of the following expressions. Write your final expression as the product of two binomials, parentheses, careful on D. All right, so this is my point, right? If we were looking, a couple lessons ago, if we were looking at a problem, let's say, that looked like this, I'm just going to throw something out. If we had something like this, 3 times x plus 3 times 7, okay, now again, this isn't part of this problem, but just like roll with me here. If, a couple lessons ago we had our polynomial written as 3 times x plus 3 times 7, you'd then say, well, 3 is multiplying x and 3 is multiplying 7, so I could factor that 3 out and write it as 3 times x plus 7. Now, 3 is a monomial, but that's really just means that it is a very, very simple mathematical expression, if you will. When I look at this particular problem, what I see is x times 2x plus 1 plus 7 times 2x plus 1. And sure, 2x plus 1 is more complex than the number 3, but it is still just a thing, right? It is just a thing. So I can rewrite letter A as 2x plus 1 times x plus 7, right? Because, if I wanted to then multiply it back out, I could do 2x times x plus 2x times 7, and I'd be back to here, all right? Point is, greatest common factors don't need to be monomials. They can be binomials, they can be trinomials. They just have to be the same factor here as what they are here. I'm sure this is probably pretty easy for you visually, so why don't you go ahead and try letter B on your own? All right, well in this case we have an x minus 2 times 5x and an x minus 2 times 4, or times negative 4. So I can rewrite this as x minus 2 times 5x minus 4. Right? Absolutely no different than, a common factor of 3 or 3x or 5x or anything like that. The common factor just happens to be a binomial. All right, now we start to get into ones that are a little more complicated. Let's take a look at letter C. Here we have x plus 5 times x minus 7 plus x minus 7 times x plus 1. All right, well again, the plain fact is, even though this is a little bit more complicated, right, I've got an x minus 7 that's multiplying an x plus 5, and I've got an x minus 7 that's multiplying an x plus 1. So now I can rewrite this, and I should be a little bit more careful here, as x minus 7 times x plus 5 plus x plus 1. Now, the directions were very specific. They said rewrite each expression as the product of two binomials. Well, this is a binomial, but right now this is not a binomial. Now keep in mind, addition is associative and commutative. So really, these parentheses at this point are kind of irrelevant, and I can rewrite this as x minus 7 times x plus 5 plus x plus 1. And now I can gather like terms in that second more complicated parentheses. X plus x is 2x, and 5 plus 1 is 6. And I've got x minus 7 times 2x plus 6. Awesome. Now remember, this problem said, be careful on letter D. All right, let's do letter D together. I've got 2x plus 8 times x plus 4 times x minus 2. times x plus 4. Fantastic. One thing that's very clear to me is that common binomial factor of x plus 4. All right, so I can start by factoring that out. And I'm going to do this double parentheses business. I've got 2x plus 8 minus now x minus 2. And here's where that care must be taken, right? Addition is associative and commutative, but subtraction not so much. So now, in order to remove the parentheses inside of here, the parentheses around the 2x plus 8 are doing absolutely nothing. But here, right, I need to distribute that subtraction through the parentheses, giving me a negative x plus 2. I can now combine like terms. 2x and negative x give me a single x. Positive 8 and positive 2 give me a positive 10. It would be very, very easy in letter D to write this as 2x plus 8 minus x minus 2. Right? And therefore giving me an x plus 6 down here instead of an x plus 10, but then the two expressions would not be equivalent. All right, now we haven't done factoring by grouping yet, but strangely enough, we've actually done sort of the tail end of it. Let's take a look at exercise number 2. Write the expression x plus 3 times x minus 4 plus 5 times x plus 3 as the equivalent product of binomials. Test this equivalency with x equals 2. So yet again, this problem is just sort of somewhat similar to what we did in exercise 1, but we keep wanting to emphasize that what our final answer is an expression that is equivalent to this one, and we're going to test that equivalency with x equals 2. So the first thing I want you to do, what we just did in exercise 1. I want you to write this more complicated expression as the product of two binomials, and then we'll go through maybe the testing together. All right, here we go. Well, the first thing that I can note, right, is I've got that common binomial factor of x plus 3. So I'm going to write that x plus 3 down, and now it's going to be pretty easy. What do I have? That's multiplying x minus 4 plus 5. And maybe I should have put a parenthesis around the x minus 4 at first, but there's no real hazard there, so I'm going to have x plus 3, a negative 4, and a positive 5 end up giving me x plus 1. Now, if I've done this correctly, what that means is that not just for x equals 2, but any value of x that I substitute in here will give me exactly the same thing as when I substituted in here. And again, I hope you understand a little bit of why we're doing what we're doing, given that this expression is much simpler and easier to work with than this expression. But let's test the equivalency, right? And why don't we go ahead and do this together? And we'll test x equals 2, and let's first put it maybe in the original, right? So if I put it into the original, right, what I'll have is I'll have 2 plus 3 times 2 minus 4 plus 5 times 2 plus 3. I'm just going to do some arithmetic here. That's going to be 5 times negative 2 plus 5 times 5. 5 times negative 2 is negative 10. 5 times 5 is 25. Equals, and that equals 15. Now, if the two expressions are in fact equivalent, when I take x equals 2 and I substitute it in here, it should also give me 15. So let's, I don't know if I really want to call it simplified, but let me do that. Simplified. So for that, right, that's going to be equal to 2 plus 3 times 2 plus 1, and that's going to be 5 times 3, and that is 15 as well. Right. And by the way, look at how much quicker it was to evaluate this particular expression at x equals 2 than it was the original. Additionally, you can easily identify the zeros of this expression, negative 3 and negative 1, whereas thinking about what the zeros of this expression are is far more difficult. In fact, there is no real easy way to do it. Okay, so mindful manipulations. Some very special polynomials, and I mean it's really they're special ones, can be factored by taking advantage of the structure we've seen in the last two problems. The key is to do mindful manipulations of expressions so that they remain equivalent but are written as an overall product. So I'm going to kind of show you how this works in exercise number 3, and we're going to talk about the real number properties that you're going to use, and then we'll actually start jumping into factoring by grouping. Exercise number 3. Consider the expression 2x cubed minus 6x squared plus 5x minus 15. Justify each step below with one of the 3 major properties of real numbers, i.e. the commutative, associative, or distributive properties. All right, and again, I really want you to get this, right? If I took a value of x and I plugged it into this expression, order of operations would say, first you have to do the exponents, then you have to do the multiplication. And once you've done all that, then you would work through the addition and the subtraction going from left to right. So what allows us to begin by saying, hey, I'm going to put parentheses around the first 2 terms and parentheses around the last 2 terms, and I'm going to group those together. Which of these 3 properties is that? Pause the video now and see if you can write it down. All right, well, that's the property that says if you have addition going on, you can kind of do it in any order you want, and that's what we call the associative property of addition. All right, now, right, I take this and I look at my 2x cubed and my 6x squared, and I rewrite that as 2x squared times x minus 3, and I look at 5x minus 15 and I rewrite that as 5 times x minus 3. Which of those 3 properties is that? Pause the video quickly. Well, that's the distributive property. Granted, it's the distributive property run in reverse, but it is in fact the distributive property. And finally, I look at this particular line and I say, oh, there's an x minus 3 there and an x minus 3 there, so I can rewrite all of this as x minus 3 times 2x squared plus 5. What property is that? Well, that's the distributive property as well. And that in a nutshell, by the way, is how we're going to do factoring by grouping. Okay? So let's get into that right now. Factoring by grouping. When we factor by grouping, we first extract common factors from pairs of binomials in 4-term polynomials. So we're always going to have 1, 2, 3, 4. 4 terms, all right? We're going to group the first 2 terms together and the last 2 terms together. We're going to factor a GCF out of each of them, and then we're going to cross our fingers that when we do, we then see a common binomial factor. If we don't see a common binomial factor, it means that factoring by grouping just simply doesn't work for that polynomial. All right? So this is a very specialized form of factoring. Just like you can't use the difference of perfect squares on a trinomial, you can't use factoring by grouping on all 4-term polynomials, except for the ones that we're going to do today, because that's the whole point of the lesson. So let's see how this works in exercise number 4. Use the method of factoring by grouping to completely factor the following expressions. Now remember, to completely factor means to not leave anything that can continue to be factored. So let's really walk through letter A together. We've got 3x cubed plus 2x squared minus 27x minus 18. All right, so the first thing I'm going to do in this particular problem is write down an equal sign apparently, and then I'm going to group the first 2 terms, 3x cubed plus 2x squared together, and I think I'm going to put a plus and write down negative 27x minus 18. All right, so I'm going to group the first 2 terms together and the last 2 terms together. I'm going to completely ignore those for a moment, and I'm going to just look at 3x cubed plus 2x squared, and I'm going to just ask, can I factor a GCF out of that? And the answer is yes. Not a numerical one. The 3 and the 2 share no common factors other than the number 1, but the x cubed and the x squared means that I can rewrite this particular thing as x squared times 3x plus 2 plus. Now, if factoring by grouping is going to work, then whatever I factor out of this has got to also leave me a 3x plus 2 inside of parentheses. So I look at my 27 and I look at my 18, and I immediately recognize that 9 divides into both of them, most certainly. Now, if I factored a 9 out of both of them, and don't write this down, okay? Just trust me. if I factor out a 9 from both of them, I would look at something like this. Plus 9 times negative 3x minus 2. Now that's close, because here I have a positive 3x plus 2. Here I have a negative 3x minus 2. So it's close. It's almost what I want, but I really, for this method to work, need these two to be the same. And so, instead of factoring out a positive 9, what I'm going to do is I'm actually going to factor out a negative 9. All right, because if I factor a negative 9 out, right, negative 9 times positive 3x is negative 27x, and negative 9 times positive 2 is negative 18, and now I have 3x plus 2 there, and I have 3x plus 2 there. So I can now factor this as 3x plus 2 times x squared minus 9. Now sometimes at that point, you're done. And in exercise 1 and exercise 2, we were done at that point. The only reason we're not done at this point is it says completely factor, and x squared minus 9 is an example of the difference of perfect squares. And because of that, right, we can continue to factor it as 3x plus 2 times x plus 3 times x minus 3. And that's it, right? 3x plus 2 times x plus 3 times x minus 3. All right, let's do another one of these together. Let's take a look at letter B. 18x cubed plus 9x squared minus 2x minus 1. Fantastic. All right, with this one, again, what we're going to do is we're going to start off by grouping the first two terms. 18x cubed plus 9x squared plus negative 2x minus 1. Awesome. Okay, so now I look at 18x cubed and I look at 9x squared. I note that both 18 and 9 are divisible by 9, so that's part of the GCF. And I've got an x cubed and an x squared, so I can bring an x squared out. So I can pull out a 9x squared and I'll be left with 2x plus 1. Now, before I even kind of like move on, right, notice that 2x plus 1 and notice a negative 2x minus 1 there. I can make those two match if I factor a negative 1 out of that expression. So I factor a negative 1 out and I'm left with 2x plus 1 in here. Right? Now I'm really back to exercise number 1. All right? I see a 2x plus 1. I see another 2x plus 1. So I factor that out. 2x plus 1, 9x squared minus 1. The question now becomes, can I factor the 9x squared minus 1? Almost always in this case, if you can factor, big if you can factor, it will be by factoring the difference of perfect squares. The difference of perfect squares. There will not be any trinomials or any more GCFs. You've already taken care of the GCFs in that portion. Okay? And this one, in fact, can be factored as the difference of perfect squares. That'll be 2x plus 1 times 3x plus 1 times 3x minus 1. Notice that with an x cubed, we're oftentimes getting 3 distinct factors out. Oftentimes, not always. So let's keep going. What I'd like you to do is pause the video right now and see if you can tackle letter C. Now you might be thinking to yourself, whoa, 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 that's got an x to the 5th in it. All right, but it's still the same idea. What I'm going to begin with is I'm going to group this x to the 5th plus 4x cubed. And at least there's no negatives, 2x squared plus 8. In that first set of parentheses, I can factor out an x cubed, which will give me an x squared plus 4. In the second one, the only thing I can do is factor a 2 out, but that'll also give me an x squared plus 4. And then I can factor out that x squared plus 4 times x cubed plus 2. Now, it would be very, very tempting to look at the x squared plus 4 and say, oh, I'll factor that into x plus 2 times x plus 2. Well, that won't work, right? Because x plus 2 times x plus 2 is x squared plus 4x plus 4. Or maybe x plus 2 times x minus 2. Nope, that would give me x squared minus 4, right? X squared plus 4 cannot be factored. Neither can x cubed plus 2. Both of these cannot be factored. They are both what are called prime. And just think of it this way, they don't fall into any of our categories. They're not GCF, they're not trinomial, they're not the difference of perfect squares. That's all we got right now. Eventually in this course, we're going to have something called the sum and the difference of perfect cubes, but even that one doesn't fall into that because 2 is not a perfect cube, all right? X cubed is, but 2 isn't. All right, why don't you go ahead and try letter D? All right, this one's kind of a little more conventional, no x to the 5th sitting there. So I'm going to break this into 5x cubed plus 10x squared plus 20x plus 40. In the first set of parentheses, I can factor a 5x squared out of both of them, giving me x plus 2. In the second set, I can factor out a 10, giving me, factoring out a 20, giving me, I still can't seem to get this right, giving me x plus 2. I gotta have these two match up. If they don't, I can't use factoring by grouping. And that gives me x plus 2 times 5x squared plus 20. Now, it's tempting to think, oh, we're done, because, x plus 2, that's good. 5x squared plus 20 is good. And yet, remember, they said to factor completely. And the 5x plus 20 actually still has a GCF, right? Because both the 5 and the 20 are divisible by 5, we can rewrite this as x plus 2 times 5 times x squared plus 4. Now, although I don't really have a problem with it written that way, most of the time an answer won't be left in that way, and actually that 5, that numerical GCF, will get moved all the way out to the front, and it'll look something like this. Now you might say, well, why did we end up having that weird GCF there that kind of came out at the end? If you look at the original polynomial, this thing, 5x cubed plus 10x squared plus 20x plus 40, notice the 5, the 10, the 20, and the 40 are all divisible by 5. And we could have actually factored that 5 out right from the beginning, and then gone through the process of factoring by grouping. Or we can do factoring by grouping, and at the end, if either one of our two binomial factors has a GCF, we can pull that GCF out, all right? Factoring is factoring. It doesn't really matter what steps you do it in. Okay, let's take a look at exercise number 5. Consider the expression x squared plus ab minus ax minus bx. How can you rewrite the expression so that the first two terms share a common factor other than 1? All right, because right now x squared and a times b, they don't share a common factor. So how could you rewrite this whole expression so that they did share a common factor? And side note, there's two different ways to do it. Pause the video now and think about this a bit. Well, one way to do it, simple enough. One way to do it is to rewrite it like this: x squared minus ax minus bx plus ab, right? In which case, the first two terms share a common factor of x. Or I could have had x squared minus bx minus ax plus ab. I'm putting the plus ab at the end because it has no x in it, which is really truly the variable of this problem. But again, you could do it like this. It would have even been okay to do something like this. That would have also been fine. All right, there's lots of different ways to do this so that you've got a common factor in the first two terms. The problem is, the way that it's written right now, if I were to group it like this, which would be fine, to group it that way, there would be nothing I could factor out of the first two terms, in which case I'm dead in the water with this factoring technique. But any one of these would actually let me proceed. So grab one of them and let's do letter B. Write the expression as an equivalent product of binomials. All right, awesome. Right, well, grab one of these and see if you can factor it using factoring by grouping. All right, well, if I use this particular one, and let's say I group it like this, with a little plus between them, I can factor an x out of the first one, which will give me x minus a, and I can factor a negative b out of the second one, which will give me x minus a. Now, maybe pause for a moment, right? If I factor that negative b out of this one, because it might be tempting, oh, I see a b there, I see a b there, just pull out a positive b. Again, the problem is then I'd have negative x plus a. But right, negative b times x is negative bx, and negative b times negative a would be positive ab. And now, of course, what I see is a common factor of x minus a, and that's all multiplying x minus b. And the remarkable thing is, no matter how you write it, whether you wrote it like this, or this, ultimately you get that as your answer. All right, a little bit more of a symbolic one with absolutely no numbers, except for the 2 on that exponent. All right, more work with zeros. We can find the zeros of an expression similar to how we found them in the previous lesson. When we have a cubic polynomial, this often results in 3 distinct zeros. And let's take a look at that in exercise number 6. Consider the expression x cubed plus 5x squared minus 16x minus 80. Letter A. Factor this expression completely using factoring by grouping. Awesome. Well, why don't you go ahead and do that? This is a pretty straightforward one. Pause the video now and factor this completely by using grouping. All right, let's do it. So first things first, I've got x cubed plus 5x squared. Then I'll add to that negative 16x minus 80. In the first set of parentheses, I can factor out an x squared, leaving me with an x plus 5. In the second parentheses, I can factor out a negative 16, also leaving me with x plus 5. I can then rewrite this as x plus 5 times x squared minus 16, and I can factor that x minus 16 as the difference of perfect squares, x plus 4 times x minus 4. All right, there we go. And x cubed leads to the product of 3 binomials often. Not always, but often. Now let's take a look at B. Based on A, determine the zeros of this expression by inspection, i.e. the zero product law. Verify using a table on your calculator with the original expression, and we'll take a look at that in a moment. But what I want you to do is I want you to just look at this and say, well, what would I substitute in here to get a 0? Here to get a 0, here to get a 0, and then we'll verify that on our calculators. All right, well, those 3 zeros should be x equals negative 5, negative 4, and positive 4. Let's take a look. I guess I gotta have to go into a graph. Let's add the graph. We're gonna have x to the third plus 5x squared minus 16x minus 80. Remember, we're just trying to verify these are zeros. Whoops. I definitely don't want that. I just want to hit enter. Now I'm going to go into my table. And what did I say? I said I had a 0 at negative 5. There it is. I had a 0 at negative 4. There it is. And a 0 at positive 4. And there it is. And again, what is super cool about this, and one of the big notions in math these days, is the idea of taking an expression and rewriting it in an equivalent form in order to reveal certain properties about the original expression. In this particular expression, there's nothing at all that tells me that these should be the values of x that when I substitute them in give me 0. And yet as soon as I write it as a product, using the idea of the zero product law, I know any value of x that makes this 0 will make the whole thing 0. Well, that's negative 5. Anything that'll make this equal to 0 will make the whole thing equal to 0. Well, that's -4, etc., right? And so writing an expression in a different form, in an equivalent form that reveals certain properties about the expression can be very helpful in mathematics and science and other areas. All right, let's wrap this up. So finally, a new type of factoring, factoring by grouping. And again, I want to be very clear. Factoring by grouping is a very limited sort of technique because it only works on 4-term polynomials and it only works on very few 4-term polynomials. The only kind that it works on is when you're able to factor a common monomial out of the first two, a common monomial out of the last two, and then after that, and only after that, you then have this common binomial factor in both of those two previously factored expressions, right? That's not going to happen very often. But given that is the only new type of factoring that you're really exposed to in Algebra 2, you can bet whatever standardized exam you take in Algebra 2 is going to have that type of factoring in it. All right, well, we're going to use factoring by grouping continually throughout this course, so you're going to get a lot better at it. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.